Yeah, we have two topics in chapter 3, nuclear chemistry, to finish. One of those topics is type of the reactions. Uh, we have we looked at all the decays, correct? Alpha, beta, gamma, protons, neutrons, correct? Decays. Those all those the nuclear reactions as well. But we have very specific name for two big reactions. One called is those are nuclear. Let me just correct this here. Very specific, distinct nuclear reactions. So nuclear reactions. One called is fission nuclear reaction. In this type of reaction, we have an isotope. We will bombard this isotope with neutrons, correct? Like we have the 92 here, uranium, correct, and 238, that's atomic mass or mass number. So if you bombard this one here with number of neutrons, neutrons has no charge, no atomic number, but it has a mass, atomic mass, correct? So what will happen here, you are creating out of this, you are really bombarding what? With the neutrons, you are bombarding the nucleus itself. So you get something from a huge atom, isotope atom. Uranium is very big, correct? You can see atomic mass 238, 200. You get krypton, you get barium, and you get neutrons. I'm not balancing this equation, but I'll show you how does it look like. So now you are producing three items out of this nuclear fission. So this is those type of reaction here. When you take a neutron and bombard it to bombard the nucleus of a very large isotope, this we call it fission. This is very similar to the chemical reaction called decomposition, correct? So decomposition here, that's in the chemistry composition, not nuclear reaction, composition reaction. And today we'll have the opportunity to look at those type of chemical reaction. So decomposition reaction is a chemical reaction. In the sense you have one compound and you break it in small compounds, in small other compounds. For example, you will have today the opportunity for, you can do this one here. Calcium carbonate, you take it up by heating. You can make out of it calcium oxide plus CO2. So you chop it to small, tiny molecules or compounds. This is called decomposition chemical reaction. This is a chemical reaction. However, in this sense here, we have nuclear reaction, correct? This is nuclear reaction. And we can't tell the difference. A nuclear reaction is dealing with the reaction inside the nucleus. A chemical reaction is a chemical reaction is dealing with the valence electrons, the outermost, or those electrons are found in the last orbital. That's the difference between nuclear. Nuclear reaction has nothing to do with the electrons outside the nucleus. It has to do with the nuclei themselves, whether you are bombarding both nuclei or more than one nucleus with the other nuclei, or you just bombard it with neutrons, correct? Neutrons has a mass. So, or you can bombard it with the anything has a big mass, helium, alpha radiation. You can put alpha radiation on it. So you might break it in small pieces of elements and neutrons. That's inside the nucleus. Outside the nucleus, we say this is chemical reaction. It has to do with what? With the valence electrons, with those electrons found in the last orbital. Okay, so this is fission. Fission means bombarding or chopping down the nuclei of large isotopes. So anytime I chop down or breaking down or bombarding the nuclei of large isotopes, and those, by the way, those are mostly lanthanide and actinides, by the way. So with the other elements, they are a smaller amount, but the bigger ones are those lanthanide and actinides. And if you bombard them, you break the nuclei of those isotopes, and you are producing lots of smaller isotopes, smaller elements, correct? So that's a fission. Now we have another type. Can I take this one out? So I give you the contrast between chemical reaction and nuclear reaction. Nuclear reaction has to do with the nucleus, inside the nucleus itself. The chemical reaction outside the nucleus, between electrons in the last orbital. So I will take this one here and then look at the second type of reaction. Second type of reaction is called fusion. So the first one is fission, and this is fusion, nuclear reaction. Well, it turns out to be whenever you are fusing, combining, correct? Fusion means combination. When you are combining nuclei together, you are producing what? One nucleus, which is very large. And by doing this, you generate a big type of energy outside this combination. So this is the reaction found at the sun. In our Milky Way galaxy, we have a sun. The sun, the most reaction is in the sun is a fusion nuclear reaction. So if I have here protons, correct? I mean, there are too many types of protons, and you have protons will react with another protons here. Yeah, we can take 2 and then multiply this one by 2. So you produce helium, correct? 2 and 1, 2 and 4, and this is 2. You produce helium. You are what? You are combining. This is another isotope of hydrogen, correct? We have 3 isotopes of hydrogen. This one, and this one. Those are 3 isotopes. What their names? You don't have to memorize it, but at least for the purpose of, or the sake of the knowledge itself. So let's do this one here. Here it is. This called proton, the 1-on-1, that's well-known proton. This one here, deuterium, T-R-I-O-M, sorry it is. I-U-M. This one here is tritium. 3. So those are 3 isotopes. Whenever you are combining those isotopes together, you are producing what? You are producing helium. So we can put this one here, and we can add another type of. We can say, okay, how about if I put proton? This is deuterium, correct? Deuterium here. How about if I put this one here? with tritium. This is the same thing. I get H4 and 2. Okay, and this is tritium. So all these tabs here are producing for me the helium plus a lot of energy here, plus a lot of energy. And vision is the future of really, if we can find, but the problem, the heat coming out, the energy is too huge to manage. So that's the reason it's very hard to get fusion at room temperature. This is star temperature, sun temperature, very high temperature when you combine this. It has a fusion reaction has more advantage on the fusion reaction in the sense fusion reaction you have seen. You are producing out of one isotope, how many? Several isotopes. And energy. The energy can be used and utilized for electricity, for any making nuclear bombs, whatever. However, this fusion reaction has a lot of what? Of nuclear waste. So look at this reaction and look at the reaction we have just discussed here. Just look at those and compare. Do we have anything besides helium? No. Just energy will come out. But when I look at the vision, it is vision here. And this is the advantage. Vision, I took uranium, correct? Bombarded with neutrons. I get too many particles. So this is, we said krypton. This is the first one, correct? Barium, neutrons. Now, these neutrons here can be utilizing and hitting krypton and barium, and out of krypton you produce what? Produce more isotope. So on this one here you produce more isotope. So it's those, whatever you are producing here, those called nuclear waste. So you will see most of the countries now, they are shutting down their nuclear plants used for electricity because of the fact we can utilize fusion reaction. That's in the sun. That's in the sun. Suns and stars. Not planets. Stars and suns, they have this type of reaction. But vision, we are utilizing vision, correct? We are bombarding the nuclei with the neutrons, and then we get this. You get a lot of energy, that's okay, can be used and utilized for electricity. However, then you have the disadvantage on this reaction. You have a lot of nuclear waste. And in some areas, when I was in Europe until now, some areas, I'm talking about Germany, they don't allow in some areas the people, the small towns or small villages, they will not allow the train with the nuclear waste to be dumped inside their backyard. They will come, the whole village will come, or the whole town, small town, and then just putting themselves in front of the train. The train cannot go and kill them. There's thousands of people blocking the road of the train, filled with a lot of nuclear waste. So this is a problem with the nuclear. So Germany shut down, I think, almost every nuclear plant utilized electricity, from the fact that it's just too much of nuclear waste you have to deal with. Are you following me here? And if you have an earthquake, you dump them somewhere in the ocean or in the mountains, in the caves. But if you have an earthquake and those nuclear waste are coming out, the isotopes, they will leak into the tabular reservoirs and contamination of the tabular inside those rivers, ponds. That's killing the all marine life, including the humans, because we are utilizing this tabular for drink, correct? So that's the major disadvantage of this fusion nuclear reaction. the vision, I mean the vision one. The fusion is very nice, clean, give you just helium. But the problem with it is you can't utilize, you cannot control the heat. The heat is huge. It's the heat of a sun. It will melt all the elements we have. So we don't have element to withstand the heat of the sun. So therefore, it's if we find a way of technology to find an alloy or somehow fiber, I mean, a combination of elements that can stand the heat out of this combination reaction, then we can utilize it and it will be a big revolution in the electricity. Almost electricity will be what? Will be free for the whole universe, I mean for the whole earth, because that's a very simple reaction is utilized every day, every second, every minute in the suns and stars. Are you following me here? We finished those two types. And we finished the decay, all the decay, remember? The decays, we did the worksheets on that. So now we'll go for the last one here, which is called half-life. And then I will add calculation to that. Half-life of an isotope, okay, half-life of an isotope is half of the mass. The half-life, when I say half-life, is half of the mass being what? Being decayed. And that's what's happening whenever we have nuclear waste or we have nuclear reaction. Then the problem is we have to know with what type of isotopes we are dealing with, because some of the isotopes, they have half-life of millions of years, thousands of years, some of them just one day, correct? So those are sitting around us for hundreds of years. That they can cause a lot of problems. So that's what I mean half-life. And I would like to see that's here. Let me just take this one out. This is just the nuclear fission bombarding the nuclei. So you are producing what? You are producing this. At the beginning, you are producing those here. Look. See? You are producing this and this plus energy, correct? Then you are producing this and this and this. Then you're starting producing more and more nuclear waste. And this is just type of the fission reaction. So the other reaction before we go to the half-life, let me go for the half-life here. This is the half-life reaction here. You can see it. Maybe can you see it? This is a small tiny amount. I can make it bigger so you can see the reaction here itself. Oops, it went out. Can you see it, guys? That's a fusion. So you don't produce any other nuclear waste. You produce just helium. That's I told you all the combinations are available. So that's tritium with deuterium together to get helium and neutrons. So, and we'll go for half-life. And I would like to show you in the half-life here a table how long it will take let me just look at the um, You might have not have it here, but if not, then I can post it for you. But that's a half-life. So you see, you started with that's full mass here of this isotope. As the time goes by, half of the mass will be diminished. Every time, half of the mass will be diminished. I'll show you the calculation, but the problem is I want to show you how bad those nuclear waste, because they can last for thousands of years. So let me see here if we can. I think we have it here. Yes, can you see this? I'll make it bigger again. Here it is, guys. I'll go back then and make it smaller. So here we have uranium is the isotope with the atomic mass 238. You know half-life of it? How many years it will last? 4.5 billion years. So if you get a reaction, nuclear reaction, and you have a leakage of uranium inside the soil or inside whatever the ponds or rivers, you can tell you will have this uranium there sitting, unless you are clean it, sitting for 4.5 billion years. So that's the problem with most European countries. They are getting out of this nuclear fission reactions to get electricity. So now you can get electricity cheaper from the wind, okay, from the waves, from waterfalls. That's cheaper and cleaner. But with this here type of situation, some of them is very, 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 I mean, within 1 hour is gone. Some of them, they get you billions of years, hundreds of years. Some of them even in minutes, 25 minutes. So carbon 16, carbon atomic mass 16, seconds, not even, but the carbon 14, 5,730 years. So you can tell that this is a big issue whenever you have a nuclear waste and you are dealing with isotopes that have large half-life, so they will stay with you according whatever they're there. So they will not break their masses in half. You see, in that amount of time, will take them to go to the half of the amount they started with. If you have a nuclear waste like uranium, 10 grams, okay, half of this 10 grams, 5 grams. So from 10 to 5 grams, you need 4.5 billion years. Are you following me here? Unless you clean it, unless you have to clean it. And cleaning nuclear waste is not that easy. It's not that easy. So in Germany, they just shut down all the nuclear plants that producing electricity. It's not worth it because the way you are cleaning it and all the stuff is too expensive. It's not, and the health issues coming out of those nuclear waste anyway. So let's go for the worksheet here I put for you. This is the worksheet here we have. This is an iCollege, by the way. Among the worksheets I put for you there for this chapter. So this is the formula I want you to memorize when it comes. Is it coming in the final exam? Yes, it is coming in the in our quizzes, coming quiz and exam. Yes, this is what will tell you that the mass of the whatever left over. Right? We started with the mass. That's the starting material here. This is starting mass, or sometimes they call them initial. Correct? So, and starting mass. I started with 5 grams, and I know what's the element, what the isotope I'm dealing with. I know its half-life recorded by experiment in the tables given to me. I want to see how much left out of this isotope after whatever time I want to put to myself. Final mass. So initial mass, starting mass, and final mass, correct? So we have initial or starting mass and final mass. So those are 2, and then multiply by half because we are dealing with half-life time. And the n is really number of cycles. Here it says, or number of half-lives. Number of cycles will be total time given multiplied by the half-life. So let's do, and I did this worksheet here. I work it for you guys. It's there in your worksheets. The answers is given by the author of the worksheets, but it's not showing the details on how to solve those type of calculations of the half-life. So can I take one out? Take it out? So this formula, you have to put it, for the time being, put it in the side or print it out, whatever. So whenever you have half-life calculations, please use this formula here. So now, as I said, the author is not showing you how to do those. This is my handwriting. The author gave us or had given us this answer, but did not show how is coming to this answer. The answer is correct, but it does not show the steps. So I did this in my handwriting. I did for you the steps how to do the reaction. I would like to do 2. So those are 5, I think, or let me see how many of them. Yeah. So look at those 5, and yeah, 5. Look at those 5 and tell me which one you like to go through. We'll do 2 of them, and then you can do all those by yourself. And there are a lot of worksheets inside how to calculate. So we have 1, we have 2, we have 3, 4, 5. Which one you like? The whole thing is, sometimes they ask you, and we have to know about this. Let's go back to how many sub-formulas I can make out of this? How many sub-formulas I can make out of this? Don't let me down. 3. So this is 1. This is the one, correct? Second one, not 3, but let's look. Second one is mi, correct? Equal to, that's the initial one. The initial one will be looking, the final one divided by half over n. This is another what? Another sub-formula from the main formula. What's the second one? N, correct? So n we have to watch because it's an exponent, correct? So whenever you have exponent and you want to get this exponent by itself, you have to use the anti-exponent function, correct? So if you are dealing with power of 10, for example, you go for log. If you are dealing with ln, you go for the e function. So let's do it together. So we will do first, it is mf over mi, correct? This is one by itself, equal to half over n. Correct, guys? That will not come in the final exam and it cannot come in my quiz, but at least you will be able to do it. So now I want to isolate what? N. So I can use the logarithm log or ln. So either or. So I can use log or ln, either or. So ln of m final over initial here equal, and then you have exponent, correct? N ln half. Can I get the n now? Yes. N will be ln final through initial divided by ln of half. So now we have two sub-formulas after the one main formula. Again, this one will not come, but at least you know, always remember this, always there is main formula and there are some sub-formulas out of this. So now let's go back and look at, we'll do one that has one that has MI initial, one has MF final. So we'll do, how about this? So this one here, number 5, it asks about the initial one, because that's the MI. And then we can use or the 3. 5 and 3 is the same. They are asking for the initial, correct? And we have the 1. So 3 and 5 initial. So then 1 and 2 and 4, they're asking for the final. So let's take whatever you like. You like anyone. So this worksheet, I did work it for you, as I said. So let's look at this. First one. Let's look at the first one. So first one, you have a cobalt 60. Half-life, how many? 5 years. Is used in cancer radiation treatment. If a hospital purchases a 30-gram supply, how much would be left after 15 years out of this 3.75 grams? How many? So if I have 5 years, correct half-life, and I have 15 years, how much will be left out of this cobalt 60 after 5 years? I can calculate, correct? So whenever you are using it in the hospital or in your lab, so you know how much it will last. So half-life is 5 years. So and the total years, you won't see total time is 15. So the total time 15, you have to, this is in years, and you have to multiply it by multiply it or divide it by the half-life. Half-life is 5 years. So it's 1/5. 1 half-life, 5 years. So how many we have? N equal 3. Those 3 cycles. 3 cycles. So it chops itself in 3 cycles, in 3 steps. Correct? So the 30 gram will be diminished in 3 cycles. So the first cycle starts with 30. So then it will go 15, correct? And it go 15 further than 7.5. And then the last third cycle will be how much? 3.75 grams. You can do it this way, or you can just plug it in. M final. This is the initial here, M initial. The N value is 3. So you calculate the whole thing, and it will come to the answer 3.75 grams. So how we get N? N is the total year, the total time, multiplied by the half-life, or 1 half-life is 5 years, multiplied by half-life. So you get N. After you get the N, you just do the whole calculation together. Let's take number 2. I have plutonium. Plutonium is like, it's used like a parent and daughter in the nuclear plants. They use uranium and plutonium, so for electricity. So 239 half-life of plutonium 239 is how many years? 24,000 years. How many? Uranium is 4.5 billion years. So it will take forever to get it out. if the original sample is, this is Mi, correct? How much plutonium isotope 239 remains after 96,440 years? So total years, how many? Total time? So this is the total time here. And then the half-life, how much? 24,110. So you get what? You get 4. That's your N, number of cycles. So you have 4 cycles. 1, 2, 3, 4. The first one, we have 3 cycles. 1, 2, 3. This is 4 cycles. It goes, each time you go half of the mass, half of the mass, half of the mass. So you have 4. Then you just plug in the amount you have. You started with 100 grams. This is your what? I put the decimal there. 100 grams, that's Mi, the initial mass. Multiply by half over 4, exponent of 4. You do the calculation, it came out to be 6.25. And this is the same answer the original author did. So the same answer. So if you look, this is the author here, 6.25. And we got the same he got. So we got this with this. And in each of those steps, we consider what? We consider our, somebody will tell me, come on guys. What's all in this calculation is very important. You'll not believe it. That's the first lab we did. What's the first lab we did? Significant figures. Significant figures. So it's very, very important to watch those significant figures. Are you following me here? So we have here, how many significant figures we have? 24,110. How much? Come on. Today is not Monday, correct? Today is Wednesday. Today is Wednesday. How many? 4. Correct. Correct. That's an evidence today is not Monday. How about this one here? Don't tell me it's a Monday today. How much? 3. Correct. Why is 3? The decimal is present, and those end zeros comes after whole number 1. So 2 conditions are met at the same time. So that's 3. Correct? That's 3. So, and how about this one here? Don't tell me it's Monday today. How much? 96,440. How much? 4, not 5, correct? 4. So when you, all in all, you do all your calculation, so you have to come up with 3 sig figs here. Because then the 4, this whole number has nothing to do with sig figs. Correct? Exponent has nothing to do with the sig figs. The main thing is the one with the decimal. So our answer is correct, 3 sig figs. I'll take the last one, number 5. As I said, it's straightforward, just simple calculation. It's not really difficult. Okay, let's take number 5, and then we'll conclude this chapter. We'll go for chapter 4. Okay, guys. Okay, number 5. I have carbon 14. Somebody will tell me how much is the half-life we saw a couple of minutes ago. How many years you think? Is he there in front of you? 5,715 years. That's we saw it a couple of minutes ago, the table. So carbon 14, how about carbon 16? We saw just a couple of minutes ago. How much? They're all in the seconds, correct? Let me see if you are still. Carbon 16, how much is it? Oops, sorry. I think we're still in the aftermath of Monday, I think. Carbon 16, how many? Short living. Less than even 1 second. And it's gone. Are you following me here? However, the 14 comes about 6,000 years. Roughly 6,000 years. So you can see the difference. And that's very nice to know, because we need really to know this. So let's go for, again, number 5. Let's do number 5. So Number 5, we have, this is the half-life of carbon-14, correct? And we have, if a sample today, the keyword, look at the keyword here. Today is what? MI or MF? Final or initial mass? Now, come on guys, don't let me, you are letting me down. MI, initial, that's you started with in the past. Started with in the past, last week, last 3 days, whatever. Today is a current, is a present time, present tense. This today means now. That's the final thing. So M, the keyword, always look the keyword today, yesterday, or today, tomorrow. That will give you the hint of what is this is all about. So the M final is this amount here. How many sig figs we have? 0.0060. How many sig figs? How many? 3? 4? Come on, guys, what is the significant figure of this number? Come on, we said 3, we said 4. Let's open the auction here. Somebody will go for another price? No. It's not sold for 3. Somebody, let's open an auction. Say loud, loud. 2. Come on, guys. This has 2 sig figs. Come on, guys. Why? This is decorating 0. Decoration. This is locating 0. There is no whole number here up front. None. So this is not significant. This is not significant. The only significant one is this 0. Why is this? Because the decimal is present and it comes after whole number. So how many is this? 2. Come on, guys. This sounds like Monday today. I'm disappointed here. But anyway, so let's go back. So now we have total of years. How many we have to use? It just have been present in the sample 11,000 years. So we have the total years is 11,430. That's the total time. The half-life is 5,715. Correct? That's the half-life. Always total time. Total time here. And this is half-life. You divide by the half-life. So then the answer is 2. So you have this final. And this initially you don't know. And this is the 2 over of square. Work it out. And you end up with M initial is equal to, if you look at this, this is 1 over 4. 4 will come there. So it is 0.24, 2 sig figs. Answer is this one here. You know how to do it. That's easy. So I showed you here. So when you take this one here, square this one here, this one here. When you square this, what your answer will be? This is 1 over 4, correct? So this is what? 1 over 4. 1 over 4 multiplied by mi equal 0.060. So just cross multiply, take the 4 here. So that will give you, oops, that will give you this calculation. Mi is 0.060 multiplied by 4 give you 0.24 milligram, correct? And the answer here is correct. So all the answers, I worked out all the answers. It came out really correct, except I think for I think number 4, the sig figs is not really correct. So mine is not correct either, because here you have Here you have 2, correct? And the 40 here, 40 days, correct? No significant figure. Here you have 2, correct? 8.0. So it is because this is one sig fix, this is 2, 5.0, correct? But this is will come out to cycle, so it will come up to this one here, and the grams is 160. Okay, I see why. My answer is correct because 160, I put a decimal here. I added decimal. So I added here, look, I added a decimal. We have to add decimal there, so to put emphasis on the decimal here too, put significant figure emphasis on this. And the answer is 3 sig fix. My answer is correct. His answer is correct, but it's not correct for sig fix. Correct? It's not correct for sig fix. Even if he considered this one without decimal, this is 2 sig fix. And he put just 5 milligrams. That's not correct. But all in all, the worksheet is very good. You can look at it, and there are many worksheets on the web and inside the college. And this topic will come in the final exam and the quizzes and the quiz and exam we have. So this will conclude chapter 3. We'll go for chapter 4. So I'm shut down the recording here.